Hi everyone, I hope you can hear me well. Today I'm sorry I can't turn on my camera, but from the next time I hope that you will be able to turn on your camera and I will turn my camera on. And it will, okay, I will talk about it a bit later. Just 1 second to collect all other participants. So I think it's time to start our course. I welcome all of you here. As the course name is Model of Sequential Data. We'll start with the brief introduction of the course. Then we will move to the basic things about time series prediction and what you should know about it if you want to do some kind of time series forecasting without any or almost no neural networks. So let's start. If you have any questions, please write something, or it's even better if you turn on your microphone and ask these questions in person, because it's kind of hard to give lecture and I give no feedback from you. So this is the only and the right way to make my presentation and overall course better. So let's start. Right now, the course team consists of me, Alexey Zaitsev, assistant professor at Skoltech, and Evgenia Romanenkova and Rodrigo Rivera. Evgenia Romanenkova is my PhD student, and Rodrigo is not a PhD student anymore, but he has a position of, I suppose, researcher or junior researcher in Skoltech. Also, it's important to know that we have not only the left side of the slide, but also the right side. So I hope that you will actively participate in the course and will help to make the course better. I hope, the Skoltech students that can eligible to attend this course. Okay, the general course info will follow in a few minutes. So we say that it's a 3 credit course. It's not like very easy 3 credit course, but it's not like very hard otherwise. This term we have lectures on Tuesdays and Fridays from 9 a.m. to 12 a.m. We have lecture, then we have a seminar. So it's like the common structure, 1.5 hours is a lecture, then we have a short break, and then we have a seminar on the topic related to the lecture. Sometimes you'll diverge from this rule, for example, to have some intermediate project defenses and so on, but you will know about this in advance. The last lecture of the course is December 20th, and after this lecture, you will have the final project defense on the corresponding Friday, right before the new year. Okay, you can find in the presentation and in Canvas some links to see. In particular, it's important to say that everything like our docs and videos will be available in Canvas, like we usually do for courses in Skoltech. Also, we have this permanent Zoom link. It's my personal Zoom account, actually. And also, what is important that we have also a Telegram chat. I will message him to the chat in Zoom, so you can join. It's kind of a convenient tool for communication. So please use this Telegram, but use it carefully. Please don't spam and do other things you shouldn't supposed to do. Also, a bit later, we will have a Notion page on the course Right now we don't have it. We have the page of the past edition of the course from 2020. So you can imagine what it will be the next year. It will be practically the same. Also, what's important about the course is what is the conditions you pass this course on. We have two main type of assessment activities that give you some credits, some scores to count in the final grade. The first big activity, like the most of the activity we have in the course, are team projects. As you can see, we split this project to parts related to that we don't want you to do everything in the last minute, but rather we have some intermediate report, which we call the first report. And you can see the preliminary dates. All other dates are also preliminary, but I think that we shifted like 2 or 3 days in one or other side. Please be careful, but you should pay basically attention to this kind of stuff. After the first report, you have the final report. And also in addition to the report, we have activity related to reviewing your peers. So basically you will give a task, you will receive a task to grade the first report and the same story for the final report to say if it's good or not. I think this is like in line with the general idea of the course. We aim this course at more advanced students that kind of make first steps or already made a lot of steps into science. So they kind of should acquire skills related to doing science, and in particular in the area related to the models of sequential data. And if you are doing science, you understand that the main way to communicate to your friends, to your colleagues from all the world are articles and presentations about your articles, about your results. And also you understand that one of the main parts of the modern science is reviewing and reading articles of other people. So we purposely added this activity to the course. I hope that you will enjoy the reviewing process, but we will send detailed instructions later. But please be patient and remember that on the other side, there is a student that spent a lot of time to prepare the result and to prepare the report. In addition to reports, we have our project presentations, and so please be aware that you should prepare them again 2 times. First time related to this intermediate version of the report, and the second time related to the final version of the report. So this is like the core activity in the course projects that accounts for about 70% of the final grade. In addition to this, we have 7 quizzes to control your attendance and also to involve you in the lecture material to check that you view the lecture and understand what's going on in the lecture. So we have quizzes after each week. It costs about 4% each. We'll slightly adjust this number to fit into this limit of 30. More likely we'll have a bonus quiz with the number of points of this quiz, not 4%, but 2%. So these 2 activities are projects and quizzes. I give you 100% of your final grade if you do everything right. Also, we have attendance. It's like a bonus activity, but we grade it. So at some point during the lecture, I take a caption of the participants of the lecture, and so after all, we have some grades for like 1.5% for each of the lecture in the course. So it's like things I will do right now. And so you will see that everything is quite clear. And also, please rename yourself to the names we can recognize, because from Ilyas and Misha, I can't judge who is this guy and can't count him as a student who attended the lecture. Okay, so this is so you can see how it looks like. And also, please write something in the chat so I can check that you hear me and that you are attending and paying attention to the lecture. So I expect this to be 9 messages, like plus sign here in the chat. Okay, good. Good. Thank you. Now it's more convenient to check their attendance. Okay, so right now we discussed for what activities you get your grade, and the final thresholds for A and B, they're not defined here. We will release it soon, and this would be according to what we have the course last year, 1 year ago. So I hope it will be fair. About some details of the assessment of the assignments, we will have project topics released like in about 1 week. And the idea of which project would be to implement some article and advances. So the most of the project would be of 2 parts. The first part is to implement some results or partially implement if there is a lot of experiments. And the second part would be to add something new. And so according to this, we have these 3 main activities here. First status report is like the basic thing that you understand what is going on here. So we have the project title, problem statement, challenges, roles, and also we will add here the literature review related to this particular article. I understand that you can take something from the article you implement itself, but please be careful and focus on specific goals of your project. After the first report, you work hard on the projects, and you have the final report, like similar in the volume to the scientific article, like about 10 to 15 pages that describe methods, final results, some conclusions, and also include link to GitHub repository so we can check the code and see if everything okay or not. Note that both these activities are peer reviewed, so your colleagues from the course attendants will review what you are doing. We expect it to be similar to the review of a scientific paper at the conference. We'll provide some guides, like taking it, for example, from ICLR or ECLIR or whatever scientific conference you can imagine that has A-star ranking. And similar to these conferences, all deadlines would be hard for the reports, for peer review, for quizzes. Okay, to be closer to the actual science. And so if you are late with something, then you get 0 score. We will release all times in advance, so be careful. And as you're working in a team, I expect that 3 or 4 Skoltech students would be enough to manage this time constraints, especially if you are doing things like this during all the course. Also, we have like a single exception as we have online mode and quizzes. We say, okay, sometimes you have some very strange circumstances. You may be ill, you have to visit your grandma and try her pies. And so in this case, you can write Evgenia just after the finish of the deadline of the quiz or before it, that you want to postpone the deadline for this quiz for 3 days. This request is processed by Evgenia Romanenkova. She is in the chat, so please write to her and say that you want this quiz to be assessed a bit later. Also, we will have a specific form for your concerns about the quiz, because we understand that this is like kind of hard format, and sometimes we may be not precise enough, so we are open for improvement. But as we did this quiz, most of these quizzes last year, we expect that everything is almost okay, and the comments would be minor. Please don't abuse this kind of form and don't irritate Evgenia too much, because our goal is for you to acquire some knowledge, not to have fights about what kind of things you do, don't do, what the exact precise answer should be. Please be patient, and we'll be patient to you too. Also about like the specific project topics and team size. As we have about 18 people in the course, we expect that there will be a team of 3 or 4 students. So it would be like about 5 projects related to this course. The projects are focused on like deep learning mostly, on implementation, some deep learning approach. So you should manage that you have to assess computational resources. For some projects, Colab would be enough, but we hope that we will be able to run something more powerful to complete in time the project, because the project kind of heavy sometimes. So again, please watch carefully. About the topics we have in the course, we split the course to 2 halves. The first part is about specific models and how to deal with them. So we start discovering some basic things about time series. Then we go to neural networks. It's RNNs, one-dimensional evolutional neural networks, and the hero of the day, the hero of the last few years, for sequential data processing transformers. Then we go to the second part related to some specific problems. We start with the overall stability of neural networks, the sequential data processing, and with particular sub-problems on self-supervised methods and on distances between time series. Also, we cover important topics on event sequences and on change point detection. We end the course with a lecture by, I hope, Yulia Gusak, who is a postdoc at Skoltech, on sound data processing as an example application, and what is different between like deep learning in the wild and general models, and more specific problems one should solve if we want the model to run for a specific application. To sum up, this course is about how we should process sequential data of different types, starting from this tabular type of time series and going on with as complex data as sequences When you observe something at uneven grid, we go a bit into the area of natural language processing because it's also sequential data, but this is not our focus. If you want to master natural language processing, please visit courses by Professor Palchenko. He's very good in it, and he will cover in more details some specific topics related to this vital area of the modern artificial intelligence. A few final words that we expect for you to be strong and motivated students, and this means that you are familiar with machine learning, with some basics of deep learning. If not, it's also possible to get the positive grade after the course, but it would be harder and you should be ready to invest more time into completing the project, kind of main activity in the course. So this is the end for the part related to the general information about the course. And my question to you is, do you have any questions related to this first part? If yes, please say it loud or write in the chat if you feel uncomfortable about it. Okay. No questions. Yeah, I hope. Okay, Evgeny, this is a kind of subjective thing. I expect that if you a good CDI's first year student, it should be enough. If you train it somewhere in your life, some deployment model, not, maybe it would be hard if there was like a basic models like MNIST for like this multi-layer perceptron. But I think it would be okay. It would be okay to have background like this and to build on top of this. But okay, you understand it would be easier if you have some background, especially if we say that this course is targeted at audience that can do some science related to deep learning and machine learning. We expect some level from. Any other questions on projects, topics, on kind of specific type of course? Also, I forgot to mention that with high probability, the course will be in online mode because of the current COVID situation in Russia, unfortunately. I would be glad to see all of you in person. In my opinion, much more effective way to think about education in general, but unfortunately we have what we have. And it's like so. If you have no further questions, we can go to the main part of the course, to the information about some specifics of time series. We'll start with a very general introduction, but we will go and find about Joras. We will clarify Nikita and reveal what we can do. But I suppose it's typical for it. I don't know. I will consult with Rodrigo and Evgenia how to get access to Zoras, and is it possible for the students that are going to take a course and run some computation related to the course. But thank you, it's kind of a good question. Okay, so let's continue. And thank you again for your questions. They're kind of useful for me and for the students. So let's imagine, okay, we have like the main thing for a bank, for many industry companies is people. And so when a guy, a girl, come to a bank and want to have some loan, we have some questions to answer about returning credit, about that we should get as many data as we need to make informed decisions. And also we ask a third question on how can we improve customer experience. And like a common way to start to think about credit scoring about the application is to use tabular data, but for sure it's not the best way to have to proceed if we are thinking about the most useful part of the information of the data that then we can assess like in no time. But if we a large bank, this is our old client, we know actually a lot about him, and maybe the main point here is that he spends some money and we can see his or her spendings when he came to us for a loan application. We know that he, okay, this is like a race like Alex, 28, a man that works in retail, and we can see, for example, he refueled his car in the morning, then he went to a lunch, then log into a bank application for some reason, maybe to transfer some amount of money to his partner, and then in the evening watch some movie. If we are looking not at spendings, but also about like more general things, if we are working inside a big ecosystem. So we say that this sequence of actions actually is one of the best reflections of what people can and can do. And also maybe we can try even uncover things a man itself does not know yet by analyzing this sequential data. And also it's important to say that this sequence is important as a sequence. If you mix something, it would be a different story. For example, if you see that someone is watching movies during the day, it's quite probable that he is not working, and it's kind of risky to give a credit to a person who does not work much. Or if you see that a typical refueling of the car is early in the morning, so he wakes up quite early, and okay, all these things that we can try to process manually, we can instead try to process with specific models for sequential data and make the best decisions. And when we compare the performance of credit scoring for tabular data and performance of specific neural networks for this sequential data of web sequences, we can see that we don't need so much features. Instead, we can use only 12 of them and have Genie like bank analog for rock AUG that is higher, and this is a good thing because we want this metric to be as close to 1 as possible than what we have for logistic regression and for gradient boosting. So if we use sequential data and use the right model for it, then we can improve over more traditional methods. So in some cases, like the right choice, and it's not in some cases, one of the most important problems in banks, how to assess the credit score of a client using some data. So you have some motivation to study these things, I hope, and you can see that now the data, okay, the quality is more for time series data and so on. And so the next question is, okay, can we do some simpler analytics? And then we will proceed to machine learning after. So let's see what we can do and what's the motivation to use time series data for analytics. It's again sometimes two examples, but mostly we can say this is kind of important to do things in this way when we want to do analytics and to look at general figure. For example, we can say, okay, we have some inflation in 2020. I'm sorry, misprint here. Okay, if you don't know Russian, and you understand that you can't make any useful conclusions if we are looking at this single data points. To make some conclusions, you should understand the dynamics of the inflation. You can say that, okay, you have inflation like 4.91% in 2020, but you have something smaller during 3 previous years. So 2020 is anomalous in this way, and we should pay specific attention for our model to work and for our general bank to work and so on. So we say that the changes of time is like a good way to think about the data and about some process in general. Another example here is like the dynamics of the spread of COVID-19, and we look at Russian data and look at how many people are infected with this disease at each particular day. And for example, we can look here and say, okay, there you have the start of first wave, second wave, third wave, and fourth wave here. And so we can say that it's kind of vital to look at dynamics because, again, we have only one number, and we have, like, for example, capacities of the hospitals related to this problem that should be fit all the people that require hospitalization. Then we should pay attention to the temporal dynamic, and it's also useful to compare what we have here with what we have here. Is this wave is bigger than the previous wave? What the difference is? What is the slope, and so on? And this also dynamics we can capture with simple rules, but only if we have time series data. We can switch from macro wave and macro data to some micro data. We can look at how specific person improves, gains, or loses weight during 1 year. So in this case, we have a different representation of the data, and we start, for example, from April 2020 and finish in 1 year in April 2021. We can see that there is some weight loss here, and we can try to analyze what's the reason for gaining and losing weight. For example, we can say, okay, we have some peak here because, okay, this is like normal weight, and this direction, we can see that weight is higher than expected for this particular guy. And so if we go up and down, and we can correlate it with some activities. For example, we have this specific time range dedicated to exercising and regular diet. And we can see that in this case, the weight is lower, and it's also expected from the diet and so on. And also you can see that if we have some celebrations, then we have this rise in weight, and we have some New Year's Eve, again, it leads to gaining some additional kilos. So if we do some simple analytics on this data, we can make conclusions even for one person. So you don't need a lot of data, but if you try the data in a correct way for one person in a sequential manner, you can say, okay, exercising are good, diet is good if you want to lose some weight, but if you celebrate something, you gain some weight, okay, kind of trivial things, but we can do this kind of conclusions even from time series for one person. Another types of things you can do, and what you want to do actually if you're doing some big industrial company things, is that you want to make some decisions, and we can try to model what will be as a case in the future for some particular types of data. And you can say, okay, if you have some normal scenario, you have something like this for the quality of a portfolio of credit loans in a bank. Then we can say, if we have some coverage here, then we have some degradation of the portfolio related to people don't return credits too much. So we can say that if we take the right decision and we are doing modeling on this, we can model the dynamics in the future and say, okay, this is the right decision you made. And also it's important to see that we can look at specific points and say that we should take the decision during 1 month. In this case, it will be harmful. We have some time gap for making decisions. And in this case, it's kind of useful to look at this data as time series data. You would say that you have some time to make a decision. Maybe after that, it would be late, and something like this. If we have like a good tool to forecast the future on the basis of what decisions we make, for example, we can say, okay, we reduce the interest rate from 7% to 6%, and it's the right decision because of the general change of the economics of the country, and so on. So we see that even simple analytics, simple data analysis, sequential data is a powerful tool that lead us to more powerful decisions and some conclusions about what we are doing if we are a single man or if we are a population of a big country that suffers from COVID-19. But okay, for sure, I hope you didn't come to this course for analytics. Rather, you want to have some machine learning and deep learning experience and models related to this kind of sequential data are based on this particular data. So again, we start with, like general introduction. Why do we need sequential data, specific proceeding of this type of data? If we are thinking about tabular data and we want to make some conclusions. So we say that, okay, let's consider the simplest problem possible. We have a ball and we know the position of a ball at time t. Okay, the reasonable problem here is trying to predict the position of a ball during the next time moment. But if you're trying to do this, we don't have any particular intuition about what's going on with this ball, because we know this, okay, kind of static position, and we can say that we are uniformly deciding at what direction the ball will fly later, because okay, this direction, and all this direction are equally probable if we have no other information. We should find a source of information which will lead us to more informed decisions and to better models related to this poor ball. And what we can try to do is to use information from the past. We can say that we know the position of the ball not only at time t, but also at t-1 and t-2. And if we have this information, then we can try to make a reasonable prediction. And in this case, we say, okay, we have this dynamics. And so in the end, the ball with high probability will fly to the right. And this kind of type problem, but it illustrates what kind of information we will need for the problems that related to the time dependencies. Also, it's not only a toy problem. We have something like this when we are planning robot navigation. So we have a robot here, and we have some people that are around him. And we want for this robot to plan the trajectory in this crowd. So we can say, okay, if all people are static, it's kind of easy problem. We just go here because we have enough space here to fit the robot and to go on in this direction. But we know that the real life is more complex. Actually, we have some trajectories for each of the people. Like this. And if you have a video camera more that is mounted on this robot, we can analyze the sequence of frames and predict the position of the people later. And in this case, you'll be able to do more interesting planning of the trajectory. You can say, okay, we have this guy and this guy who is trying to prevent us to moving into the right direction. And in this case, we say, let's have a better planning scheme, like something like maybe like this. It seems like this is not an optimal path if you don't use a temporal information, but if you use temporal information, that's like definitely the best choice in this case. You can imagine similar thing with, for example, road planning in more general scenarios, for example, for a taxi. In this case, again, it would be useful to use the current information on the road and like how red is this sign for Yandex traffic jams service and so on. But also it's useful to take into account the dynamics and typical behavior, what we will see in the future. And actually, there is a lot of things to predict, and this all things are very important. For example, we can say that it's crucial to predict like what's called actually demand forecasting for some retailer, because it will depend on what we should buy and in what amount we should buy it. And actually, there is a different type of problem here. For example, yeah, for retail, we predict like how many apples will be sold tomorrow. But we can say something about more complex problem. For example, we want to predict sales of a new iPhone. I think it's a crucial problem for like retailers and for Apple in general. And it seems kind of hard problem, but it is also possible to predict the dynamics of something new we never saw before. And so it's kind of important, and it's kind of models we can use for this. Also, there is another typical problems a lot of people are thinking when they come to courses like this. The most natural like time series we see a lot is prices of stocks. Again, we have some price for Apple company, and we want to predict the prices for the next year. It's like a reasonable problem. It's an example of a problem you should not generally solve because it's too hard, because the behavior is too unpredictable, because we don't know everything. We don't have enough information to make good predictions. And it's a scenario when we try to predict like next minute, next hour prices, we with high probability will make useless predictions for various reasons. So there is some problems that it's quite hard and you should not solve them. And I hope after the course you'll have some intuition of why some problems are good and some problems are not so good, and you should not invest much time into them. Into this problem. Another problem I described before is some kind of transactions. And for example, we can look at this transaction series and say there is a fraud related to it. So you should treat this customer with a serious caution and try to stop him from spending some money that is not his. We also have a lot of problems that related to non-structured data. In this case, we can collect all those data. This data is structured, and we can imagine that input here is a table, maybe of varying lengths. But in reality, we have a lot of other problems. For example, we want to do some speech recognition, like we have some time series input and some text as a noun, and both input text and output text are not like structured. This not tabular data, structured. The same thing if you want to process natural language person data for translation or for like trying to guess does the user like this movie or not. Again, we can use as input some video, and we want to process the video to, for example, identify the type of activity that is depicted as this figure. And so we can say that this topic is quite important, and there are a lot of problems related to the processing of simple data that can be equivalent for time series, but for tabular data. But also we can have more complex data of varying lengths, of varying complexity. For example, we can even have this video frames as input. We should somehow process them with convolutional neural networks because we can't understand what's going on the video if we don't have things like this. Also, it's my question for you. Maybe it will help me to better shape the course. So I give you a couple of minutes to provide an example of time series data you're interested in, and maybe something you want to be able to solve after finishing this course. So you have about 2 minutes to write this kind of problem in chat. So you're welcome here. And okay, I expect at least one problem from one participant of the course right now. Okay, thank you, Shakir. A good start. We can discuss later, and even now. Okay, after other people will also provide their feedback. Okay, I repeat that I expect one problem from each participant of the course. Yeah, that is in line right now. Okay, thank you. Okay, good. Okay, thank you. Okay, 1 minute from your colleagues to finish, because right now we have only 2, 3, 4, 5, 6. Okay, thank you. I hope I like your problems. Let's have a brief discussion on them. Let's start from the very beginning. Weather forecasting. It's an interesting problem, and there are some services that is related to this kind of things. For example, we can say that if you look at Yandex weather service, when you see these clouds and the rain will be here for 2 hours, it's based actually on machine learning. It was, I suppose, mainly done by former PhD students of Viktor Lempitsky, who was studying in Skoltech, Vadim. And for short terms, machine learning and deep learning can provide some improvement over classical models. But I suppose that for long terms, like for a few, if you want to predict a few days, it's kind of hard to do more accurate forecasting than the model we have. But also we can go further and say that we can try to predict how different decisions affect the climate overall. And right now in Skoltech, we have a center dedicated in particular to this problem, how to use artificial intelligence for sustainable development of our planet and of Russia in particular. About the certification is interesting problem if we can define a particular ID of using a sequence of users, and thank you, it's a good problem. About exchange rate, it's also hard because of this. A lot of people trying to predict like this exchange rates. So if you want to make some benefits, it should be better than all other people. It's kind of hard to be better than big teams of people. But we can try to make some basic things. For example, we can try to predict not the exact value, but some value with some confidence intervals that can help you to make some informed decisions. For Evgeny's problem about feature detection from stereo camera frames, I suppose that deep learning will help here, and I hope that we'll have some intuition in the end. Mental state prediction also interesting. I don't know what is the input. Okay, can you hear me, Van? No, right now. Yes. Okay, thank you for the information. Let's continue our recording. And okay, about stock prices, I discussed it. Okay, we can try to predict the variance, but it's very hard to predict the mean value for stocks. Very hard problem. About orders, okay, yes, Elizabeth, I know about this problem. What we're trying to do together, and it's also an important problem, and also related to a topic in our course on event sequences and on how to work with them. Automatic prediction of period is interesting. Don't know a particular application for this, but sounds good. Also, anomaly detection. I like this, and okay, I'm doing a lot of anomaly detection, and we will consider some change point detection and partly anomaly detection for time series too. Regarding Anton's problem, I also like it about like churn detection, about the sequences of actions, kind of natural way to see on this problem as a problem related to the processing of sequential data. Also about methods, so you mentioned a lot of problems, but also good that you mentioned not only problems, but also regular architectures. You should know, and I hope that we will cover this too, and we cover all the main things that are used right now in industry and in science to solve problems like this. So let's go on and try to go on to some methods. So basically, we will start with maybe the simplest, but maybe one of the most important problems in time series prediction is the problem of working with time series is time series forecasting. So we have data up to some year, in this case is 1961, and we want to predict something for the next year, maybe to plan your flights, to arrange how many planes you should buy, and should you build a new airport or build another terminal in an existing airport. So basically, what we have as input to our machine learning model is history until some time moment, and maybe some features we know is the next moment. And we want to predict what is going on in the future at time t. This is very basic problems. These very basic tabular features in the very beginning. So we say, for example, typically we know, for example, we want to predict some demand here, demand forecasting, and I'm sorry, I will have some. And for this demand forecasting, we have a demand during previous day, how many goods was bought yesterday, and on and on and on. And so we have this historical data that we use to predict the future. Also, we have a lot of further goods we can use, and also a lot of external factors that can be useful in this scenario. For example, we can say that we predict how many people will visit this particular shop next day, tomorrow, and we include predictions using another machine model into this model to predict by how many specific products will be purchased next day. Also, we can use, for example, weather forecast here again and say, okay, we have this, for example, prediction of 8 degrees above zero, and we can use this to predict how many people will come. Again, we can predict that there will be some rain here, and it will, this high probability, affect how many people will come to you, and so on and on. And basically, what we try to do, and what usually people doing, is to a simple reshape operation. So this is what we want to predict. This is our output, and we have everything else as input here. So we have this classic tabular data problem. When we collect a lot of data, for example, we can do the similar thing for IT-1 and corresponding inputs and so on and on and on. And so we have this table with the first row is the output we want to predict, and all other inputs are features. We can enrich the features with something we don't have in this data, but we can find it useful. For example, we can have a categorical variable related to the day of week. So it's, is it weekend or not? Is it like holiday or not? And so on. Also, it can be useful to include some derivative features. For example, we can include the dynamic, the difference between two features or two values of the same feature into like the space of the features we use as input. And it kind of useful in many cases. And so we should definitely include. But as you can see, this scheme is very close to what we often have when we are thinking about like a regular tabular data problems. The difference is that we have different types of features, different features we use here. And so we include the history of target variable. We have like this list here, like this features generated. And specifics here is that we again look at specific features related to time series and try to imagine what can be useful. For example, can be useful to have some difference here, some day of week feature, and so on. So as soon as we have things like this, we can apply any machine learning regression approach for the forecasting or prediction. For example, we can try XGBoost or CatBoost, or even try a linear model. All of them kind of useful. And particular selection, as in all other machine learning problems, depends on what kind of data we have, how many data we have, because typically in many cases in real life, we want to make daily forecasts. So we want to forecast something for tomorrow, for example, weather or purchases of champagne or beer. And in these cases, we don't have much points actually. We have 1 point at a day. So if we even have history for 10 years, we have only something like this data points in our training sample. So in this case, it does not make sense in most cases to use sophisticated approaches. Rather, we should, in a clever way, use the approaches we have. Also, it means that we should not use a lot of features because we have some thousands of features and we have only 4,000 data points. It can be harmful to make predictions like this. Also, you should note that sometimes you should carefully watch at what you are predicting and what kind of data you can use. So you should try to avoid data leaks. You should be able to say if this feature will be available when we use this model in production, so when it actually helps people can use the same feature, for example. Also, it's kind of interesting to think how deep we can dive into historical data, because sometimes something changes and we need to just drop everything before some particular amount, because there should be a different dependency, different time model. For example, we had a store here and we predicted some demand forecast here. But at the same moment, we have not one store, but also we have a store by our green friend, that also another grocery store next to your store, and definitely it will affect how many goods you sell, because some people will decide not to go to your store, but instead go to a neighbor store, and we can say that at time t, we have a different dependence, a different model we should train. And this is the case for many applications. So you use like classic approaches, but use them with caution. And also you should assess the quality of your approach. And this, like if you imagine this as time for, so this is our time t, and you have observations at each time moment. It's not a good thing to split the data in the way depicted as this figure. Maybe someone in the chat can explain why this scheme is not working for time series, or you should be use it with great caution. Maybe I can even give a bonus bell to a bonus score to this particular people who will answer this question. I don't. Okay, you can do better. I hope. Strict temporal dependence is kind of hard to think on. So why we can do cross-validation and assess the quality of the data like this? Any other ideas? Yes, Andrei, you're quite close to what I expected to do, and thank you for the answer. Yes. So maybe you provide the right answer, but explanation can be still improved. And the reason is that when we try to make some kind of cross-validation, then we should imitate usage as close as possible, usage of the model in production. And in this case, we can say when we train some model, we use data only from the past. Train past data. And usage future data. So in real life, we will train on the past. So if you have time t here, that's the past to this test, and it's okay to use this data for training and this data for test. But for this split, we are in a bad situation because our training data is from the future here, and we predict from the future. It sounds like very strange thing. So we should avoid this. Instead, we should drop this part of the data and train on the past data we have here for this particular split, for this particular test data. And so we can say that we can modify this scheme to have it like this. Also, you can see that we dropped some parts of the data because sometimes it's like a non-universal rule, not a universal rule, but in many cases it makes sense to just drop data from past far away because the dependence the model change as time passes and we are not interested like in very general dependence. Rather, we would use data from the last few years. For example, we have this COVID-19 starting, and we no longer can use data in the past. Also, we can try to make overlapping splitting, and it makes sense if you don't have a lot of data. So particular validation scheme is important. The basic idea that the difference between time series prediction validation and usual model validation is this, but devil in the details is what you should account for your particular problem. And again, please use the mind to create some useful validation scheme. Also about validation, it's always important to remember that you should pay attention to other approaches, to other baselines. And in time series, usually there is a lot of useful baselines you should compare to argue that your approach is working better. And you can see two examples, maybe the most important baselines that you should compare to. The first baseline is we predict using the last value we know from the time series. So it's okay, we have this time series and we predict like this, predict like with a constant that equal to the last point. Also, we can try to do similar thing, but average for some region and predict like this, with a rolling mean of previous values to reduce noise, but to make still simple and useful models. And this model works very good in many cases. For example, when you try to predict weather, you predict the temperature, and to predict the temperature for the next day, for tomorrow, maybe the best thing you can do without using a lot of data, computational resources, and domain knowledge is to just predict the value you have right now. The weather tomorrow would be the same to the weather you have today. And it's kind of a stronger baseline in many problems. You can imagine something similar when you're predicting demand for some good. You say that, okay, it will be similar to what we have yesterday, and it kind of makes sense because it's like the closest point to the future we have, and it has high predictive power. Another simple idea that works very good in many scenarios is to improve over the prediction using the last known value, but don't put many features. In many cases, the most useful features is the past values itself. So we say that, okay, we want to predict something here. Let's use these two features and try to construct a simple model like by t minus 1, by t minus 2, by t minus 3 with some weights. And we see that this linear regression model to predict by t with a hedge is kind of important thing, very, very important baseline that all of you I suggest to try to argue that we should do something like this. So please try it before you're saying that your gradient boosting is something very good. Maybe it's not that good. And there are some examples for this simple time series. And you can see that if we plot true values versus prediction for this baseline, we have very high R-squared values. Okay, typical for this problem. It's like 0.47 and 0.73, and both cases, I think it's very high, especially if you think about how simple these models are. And they're still very good. In many cases, you just don't need complex models. You can just sometimes use analytics. So to conclude this part, if we have the structured type of data close to tabular, then we should try to formulate our problem is. The problem with tabular data Yes, we can try to do some kind of smoothing, and it's very useful idea, especially if you see that you have a lot of noise if you're in your data. And so basically you can try a couple of ideas that seems reasonable for your problem. It's kind of similar to all other things or the like problems you solve in machine. Try starts with simple ideas and gradually increase. If you see that simple ideas don't work, only expect that you can do better with something more sophisticated. And like the main issue here is to collect the right features, and this is like the crucial question actually all the tabular data. If you collect the right features, then even simple model, not very big amount of data, can help. The best case, the best scenario is when you have only one feature and you predict on the basis of one feature. But for sure, in real life situation, it's more complex, and typically we include more features to get more accurate predictions. And so you start with simple baselines and you go on and on, you generate more features, try to use more sophisticated approaches like gradient boosting or some kind of, for example, kernel regression, I don't know. And so you compare and see if the steps you take are right and we can do better from this. So this is a very basic intro. And during the next lecture, we will try to cover more complex, but also very useful types of models. We can say like general ARIMA and also modeling that was popular in 70s and still quite useful when we're thinking about a time series model today. If we have some time to dive into the data and to construct a separate model for trend, seasonality, and all this stuff. Also, it kind of natural idea to like delegate future generation, not to a data scientist, but to some automatic tool. And like the first idea I like, but I never saw it in production, is to make some database with all time series in the world and try to use them to make some predictions. Crazy idea, but maybe interesting in some areas. Also, this is a good point to say something that sometimes we have some spurious correlations, and if you have like thousands or tens of thousands of time series, typically you observe something very, very strange. For example, we have number of virus here and global average temperature. As you can see, temperature rises and number of virus decreases because we have this inverse scale. But you can see that it's high correlation, but definitely I suppose at least that's kind of, which would be very strange if this a correlation. Maybe okay, I can find no reason why this features would be correlated. Also note that sometimes some time series is very hard to collect. For example, I heard like talk from an industry guy, and he said that they required a feature that's a forecast of temperature for some data. And it was very hard for him to find a source data to find weather forecasts for the past because no one stores them. So maybe you can think in advance when you're like collecting some features and you're organizing data storage for your problem. But also you can avoid this hard thinking, collecting very hard things. Instead, you can try to use some libraries for automatic generation of features. And maybe one of the most powerful library here is TS-Fresh. You can Google it. And there are some examples of features it can generate. For example, we have some time series in the past. We use max, mean value, median value, mean value, number of fixes calculated automatically, and on. And actually, there are hundreds of features to get. And also, this library has built-in procedure to drop some features because they are irrelevant according to what we see right now, what we see in the data. So we try to contract the feature space and have fewer features because, okay, if you have too much features, our forecast will be good and suffer from overfitting, most probably. So use test crash. And also for some specific applications, you can ask experts what to generate. For example, in some cases, it's useful to generate Fourier spectrum of your time series and use this Fourier coefficients as input features for some kind of prediction. It's not useful for all time series, but sometimes it kind of, we have some of this, for example, some approaches that is kind of equivalent to usage. So please contact experts. Also, it was the case for us for when we were doing some prediction. I don't know what we predict, because prediction actually, but basically we have data from flights of airplanes, and for one flight we have about 1 terabyte of data. You understand this actually a lot of data here. So it's 1 terabyte for one flight. And this is kind of a lot of data. We have some tens of thousands of features here. But when we go to an expert, and experts suggest to use only one feature, use this feature. And it worked like a charm. So if you know where to look at, we should definitely try to do this instead of doing this stupid machine learning with millions of features without critically assessing the result you have. So you can use this kind of stuff and it helps, but sometimes please be careful about it. And to end today's lecture, let's consider another example from industry that highlights how many difficulties we can see if you look at real problems. As a first place, we want to predict number of purchases tomorrow, what's called demand forecasting. And if you're a small grocery store, actually you don't need this stuff. You have a simple pipeline of what we are doing here. Basically, you look at what you don't have, what's typical pattern, and you try to order something, and typically it's enough. It's very hard to beat this because you don't have enough data and you don't have money and time to spend on expensive data science. But if you have a lot of grocery stores all over the world, makes sense. When we have something in between, I suppose when we have like 50 points of sales and so on, that it's okay to start to use machine learning. Before that, it's questionable. But if you have such a lot of goods, a lot of things to predict, you understand that actually it's about 20,000 of goods in a supermarket. So you need to make predictions in a fast way because you need to run like 20,000 of models each day to predict for tomorrow. Some models should be fast, and it's a problem that you should create reliable forecasts. So basically, in this case, again, I emphasize a simple baseline block. If we select the right features, then linear after regression will do our job for you. Also, when we're trying to dive deeper into this problem, we see that there is a lot of things to consider. For example, we have periodicity related like that. On weekends, the behavior of customers are different than during work days. Also, there is some important internal decisions that affect the final model and the prediction, and should affect the prediction. For example, if you have a promotion of some good, then there is definitely a rise in how much we sell in this case. Also, there is some effect related to cannibalization or GALO. Cannibalization is when we introduce a new product and older products has smaller number of purchases after it, because they're two similar products and customer wants to try something new, or at least he has a choice, and sometimes he selects a different product. Glow effect is something different. So if you buy a beer, you will buy something to eat with a beer, a cheese, for example, and so on. Also, we have some elasticity to prices. So decisions in business affect the model, and you should use it into your model if you want to create a perfect model, and there is some source for improvements. Also, we have something you can't affect, but it happens: weather, local events, and so on, so on, so on, so on. And so you should be able to deal with it. Also, we have some factors like COVID-19 on your store next door, or roadwork near a grocery store that definitely affects the sales, and so you should take them into account if you want to have a good model. And also, again, we should sometimes make informed and reasonable decisions. For example, we can have some products that have a small number of sales, and actually doesn't make sense to make a prediction for them. It's too rare, and you should use instead some very simple models for demand planning. Also, sometimes you should rely on humans and people, on their judgments. And for example, at the beginning of COVID-19, you expect that all retail models would be broken, and so we should have some backup plan what to do if our extrapolation no longer works. Because for time series, it's like a peculiarity that it's actually extrapolation problem. You try to predict the future and hope that for some reason future would be similar to what you observe now. In many cases, there is no assumption, but again, it's kind of a difference of this problem from all other machine learning problems. And also, when we are thinking about the big picture, then we should take into account that there is only a model, and actual business decision on demand should take into account different things. For example, when we look at loss function, the loss function is non-symmetric here, because if we provide too small amount of goods, then we just lost sales. If you have too large amount of goods, okay, that's on a shelf or something, or something like even not on the shelf, something out there, and we can put it later. So as you can see, when we use real problems, we should find some problem-specific solutions. We will not talk much about actually in the course. It's just like to give you a key on how we can deal with such problems if we will have something like this in the future. Also, if you look at this particular problem, you can see that it's a complex problem, and it can be more complex than you can imagine from when you look at first time. And again, when you're making decisions in industry, is only part of big business process, and you should also take into account that you're only a small part of a big company, but it's a very important one, and you should serve or work for the best for this company. I think it's the end for today lectures. We'll have a seminar in 5 to 10 minutes. I hope Rodrigo will conduct the seminar and will write to you about the exact time of the seminar. And next time we'll continue with classic machine learning models with tabular data for time series. In particular, we'll consider RIMA, trends, linearity, all the stuff a lot of people are talking when we are talking about time series, but no one actually get a feeling of why we should use this, why does it work, why it doesn't work, and what are the probabilistic assumptions behind these models. So that's all for today. Thank you all for joining the course and for joining the lecture today. I hope that we will have a wonderful 2 months related to this particular course. I am here to help. You can write me in the chat. I will try. Also, you have Evgeny and Rodrigo that can help you to gain some experience on working with time series and on work with sequential data. And so be it. Goodbye. Have a nice seminar and a nice day.